Good afternoon, class. We are looking at 3.5, the second part, implicit differentiation. As you can see, we have all the basic differentiation formulas, the product rule, the quotient rule, the chain rule, exponential rules. And now we want to look at implicit differentiation. So first, let's find out what's an explicit and implicit function. Functions expressed by one variable are defined explicitly in terms of another variable. For example, y equals x squared minus 2x plus 1, or in general, y equals f of x. That's explicit. Some functions are defined implicitly by a relation between x and y, such as x squared plus y squared equals 25, or x cubed plus y cubed is 6xy. In some cases, it is possible to solve such an equation for y. Here's an example of that. And in some cases, it's not easy to do that, or it may even be impossible. And that is exactly why we're going to go over the implicit differentiation. We start with the simplest example we can think of, which is a linear equation, 4x plus 2y equals 10. And we are going to do it explicitly, meaning we are going to first solve for y. To do that, we are going to move the 4x and then we're going to divide both sides by number 2. When we divide by 2, the left side becomes y. Remember, this is gone. Minus 4x becomes negative 2x, and 10 becomes plus 5. And clearly, y prime is negative 2. Implicit differentiation means we're not going to solve for y. We are going to differentiate as is. So for x, we know the derivative to be 4. 2y, remember, y is a function of x. You can think of it as f of x or g of x. The derivative of f of x is f prime. G of x is g prime. And the derivative of y is y prime, or dy dx. So 2 times y prime or dy dx. This is a constant which gives us 0. And there's a reason I put dy dx on purpose, because I want to again mention that they are the same. This is in Leibniz's notation, with the difference that it specifically tells us what is the independent variable. We're going to move the 4. And we are going to divide by 2. And therefore, dy dx is equal to negative 2. It's a very simple process, as you can see it. And it shows that we can do it either way. Needless to say, this was a type of question that it was easy to solve for y. But we're going to look at a case where we don't want to solve for y. Again, this is an example that can be done. You can solve for y. In fact, you can try it at home. But let's find y prime just the way it is by differentiating both sides of this. And to make sure we understand how this is going to work, we know the derivative of x squared is 2x. I want to discuss y squared, and I'm going to remind you of the extended power rule, which says the derivative of g of x to the power of n is n g of x to the power of n minus 1 times g prime of x. And remember, y is a function of x. You can think of it as g of x or f of x. Therefore, the derivative of y to the power of n is also n y to the power of n minus 1 y prime. Extended power rule, because y is a function of x. So this gives us 2x. This gives us 2y y prime, according to the formulas here, and a constant will result in 0. So we will move the 2x and we're going to divide by 2y. So minus 2x over 2y, it's minus x over y. We want to find an equation of a tangent line. We need a pair, 3, 4 is given. We also need a slope, and we already found the derivative. All we have to do, plug in the pair, replace the x with 3 and y with 4, and that gives us the slope. Now y minus y1, that means y minus 4, equals m negative 3/4 times x minus x of 1, which is x minus 3. This is minus 3/4 x plus 9 over 4. We can move negative 4, make it positive 4, which is 16 over 4. With 9 over 4 becomes 25 over 4. X cubed plus y cubed is 6x times y. We want to differentiate this. X cubed gives us 3x squared. Y cubed, again, we've discussed the extended power rule, n 3 y squared. Then you can write y prime or dy dx. Y prime is easier to write it, but either way is fine. So plus 3y squared dy dx. On the right side, I want to put a raised dot here so everybody can see that we use the product rule. It is the product of 6x and y. So the derivative of 6x is 6 times y plus the derivative of y is y prime or dy dx times 6x. And we are done with calculus here. It's extremely important for everybody to see after the asterisk next to it. And the rest is elementary algebra. We are solving for y prime or dy dx. That means we are going to bring them to the same side, and we move everything else to the other side. Therefore, this moves this way, and it becomes negative 6x dy dx. This moves this way, and it becomes negative 3x squared. So we are moving things around. On the left-hand side, we are interested in dy dx. We're going to factor that out. We notice we can also factor the 3. So it's a matter of factoring. You can just drop number 3 from both sides and divide by y squared minus 2x. And it gives us dy dx is 2y minus x squared over y squared minus 2x. The only thing I want to add is that if we move things differently here, the result may look like this, and it's the same. If you move it differently, this may look like x squared minus 2y over 2x minus y squared, which is exactly the same expression. If you multiply the top and the bottom by -1, you get this one. So that's the same thing. We want to find the derivative again. Again, whether you use dy dx or y prime makes no difference. The first thing we notice here, it's 4x squared times y. Let me put a raised dot in between. So you're multiplying 4x squared by y, you are going to use the product rule. 4x squared gives us 8x times y, plus y gives us y prime or dy dx times 4x squared. 2y squared, it's 4y, y prime. 4y, y prime, any number gives us 0. So 4x squared gives us 8x times y. Y gives us y prime times 4x squared. 2y squared gives us 4y, y prime. Any number gives us 0. If I were to write it as a fg, I can do this as, let's say this is the f, this is the g function. So you're looking at f prime g, this is g prime. Now, we are going to solve for y prime. How do we do that? We're going to put these two together and we take out the y prime. It happened that 4 comes out as well, but it is the y prime or dy dx that we are interested in. Needless to say, we are going to move this and make it negative 8xy on the right side. We're going to divide both sides by 4 times x squared plus y. This goes away. Negative 8 changes to negative 2. And here's the final answer. Or x squared plus 6y plus y squared equals e. This gives us 8x. This gives us 6y prime or dy dx. And this gives us 2y, y prime. E is a number, is a constant. The answer is u. Very straightforward. We are going to combine these two and factor the 2y prime out. More importantly, we are interested in y prime. And I move the 8x and make it negative 8x on the other side. And we are going to divide both sides by 2 times 3 plus 1. On the left side, we have only y prime. On the right side, we get negative 4x divided by 3 plus 1. So implicit differentiation, pretty straightforward. We want to differentiate this, and the very first thing we do, we put a raised up between x and e to the power of y. So the product, the derivative of x is 1 times e to the power of y. What is the derivative of e to the power of y? Let me remind you, the derivative of e to the power of x is itself. The derivative of e to the power of kx is itself times k, the derivative of the exponent. The derivative of e to the power of g of x is itself times g prime. So the derivative of e to the power of y, let me just write that. Therefore, if I'm differentiating this, I get the same thing, e to the power of y times y prime according to this rule. Therefore, x gives me 1 times e to the power of y plus, remember we are using the product rule, e to the power of y is e to the power of y times y prime times x 2y cubed 6y squared y prime. The right side is number 3 because the derivative of 3x is 3. So we are looking at let's say fg f prime g plus g prime f. And we are going to combine the two terms that involve y prime and factor the y prime out. We are going to move this term. So on the right side, we get 3 minus e to the power of y. On the left side, we factor out the y prime. And all we have to do, divide both sides by the parentheses. And that's the final answer. We want to find an equation of a tangent line to x squared y squared equals 1 at a given point negative 1 comma 1. And so we need two things. We need a pair x comma y, it's given. We also need the slope. So we have to differentiate. So I'm going to put a raised dot between these two, meaning I'm using the product rule. X squared, the derivative is 2x times y squared plus y squared. The derivative is 2y prime times x squared. The right side is a number, so it gives us 0. And again, if we were to write it out, we would say this is f, this is g. So you have f prime g prime. We are solving for y prime, so we are going to use, we are going to move 2xy squared to the right. We are going to divide both sides by 2yx squared. And as you can see, the right-hand side simplifies to negative y over x. By the way, this is the calculus step, okay? Everything else is elementary algebra. And so we want to find the equation of a tangent line. You need to find the slope. You have to evaluate this by plugging in the pair, which means you're going to replace the y with 1. So the numerator becomes negative 1, and the denominator x with negative 1, and the ratio is positive 1. Here's the notation we use. We are telling the reader that x is negative 1, y is negative 1. That's the meaning of it. Evaluate this expression with this pair, we get 1. Y minus y1, that means y minus 1 equals m, that means 1 times x minus minus 1, which makes it plus 1. So this is x plus 1, and add the 1, you get x plus 2. And that's the final answer. Implicit differentiation. Let's switch gears and look at the concept known as related rates. If we are pumping air into a balloon, both the volume and the radius of the balloon are increasing, and the rates of increase are related to each other. But it is much easier to measure directly the rate of increase of the volume than the rate of increase of the radius. In a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another one, which may be more easily measured. So what is the procedure? Number one, find an equation that relates the two quantities. Number two, use the chain rule to differentiate both sides with respect to time. So what does it mean? Related rates with respect to time, that means the independent variable is t. Everything else is a dependent variable, even x. So just for the sake of argument, as a result of this, even if you want to differentiate x, the answer is dx dt. If you're differentiating y, is dy dt. And that's why you use the Leibniz's notation to make sure your reader can see the independent variable. And I'm going to have a warm-up example regarding the same concept that was just mentioned. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? In the case of a related rates, you're dealing with an application problem, you're dealing with a word problem, and it is extremely important to see what's given, what's missing. So let's discuss that. What is given is the rate of increase of the volume. So the rate of increase of the volume of air is 100 cubic centimeters per second. What is missing? The rate of increase of the radius. At what point? When d, or the diameter, is 50 centimeters. Now, this is fine and dandy, but I highly recommend you write this in a symbolic format to have a better understanding. So the very first thing is that we are relating the volume to the radius, the volume of a spherical shape. So a piece of information from geometry, the volume of a sphere is 4/3 pi r cubed, and needless to say, the diameter is 2 times the radius. D is 2 times r. So that piece of information is from before and from geometry. Now, let's put everything symbolically, what is given, what is missing, and what we need to do. Number one, we're going to write the volume is 4/3 pi r cubed. Then this is given, the rate of increase of the volume with respect to time. That means dV dt is 100 cubic centimeters per second. What is missing? dr dt. At what point? When r is d/2 or 25 centimeters. So the volume is 4/3 pi r cubed. dV dt is given as 100 cubic centimeters per second. We are looking for dr dt when r is 50 divided by 2. Now it's very clear as to what we are looking for. All right, we want dV dt, and then we get to dr dt. So let's differentiate this with respect to what? T is the only independent variable. That's why with the Leibniz's notation, dV dt becomes dV dr dr dt. Whether you write this or not, as long as you understand what you're doing, that's fine. So what is dV dt? I want to differentiate this expression. First, I'm going to write 4/3 pi because it's a multiplier, it's a constant, it's not going to go anywhere. I'm just differentiating r cubed. So what is the derivative of r cubed with the 3r squared dr dt? So the derivative of r cubed is 3r squared dr dt. Now the 3 here and here cancel each other. We get 4 pi r squared dr dt. We can divide both sides. We want dr dt, right? We can divide both sides by 4 pi r squared. That means either divide by it or multiply by its reciprocal. Anyways, we're going to divide both sides by this expression. And that gives us dr dt. So dr dt is dv dt divided by 4 pi r squared. Now we're going to plug in. What is dv dt? 100. 4 pi. What is r? 25. We just plug in. Now it's a matter of simplification. I'm going to write this one as 25 times 25. Then I'm going to use a different color and say 100 is the same as the product of 4 and 25. So the numerator is 1 and the denominator is 25. This is an exact answer. You can use a calculator with a bunch of decimals to come up with the approximation, but more importantly, the units. So the radius of the balloon is increasing at the rate of 1 over 25 pi, or if you use the approximation and using the calculator, 0.0127 centimeters per second. I'm going to go back to this, and I want to make sure everybody understands what's happening here. dv dt, the units of the volume over the units of time. That's why cubic centimeters per second. dr dt, the units of the radius over the units of time, and that would be centimeters per second. In fact, if you look at this expression, because we have r squared here, that centimeter cubed goes away and becomes centimeters. So everything that we do with numbers, we do with units, and the units will go equal. Okay. Anybody want to read this question for us? Okay, nobody? A small rock is dropped into a lake, circular ripples spread over the surface, with the radius of each circle increasing at the rate of 3/2 feet per second. Find the rate at which the area of a circle is changing when the radius is 4 feet. So as we read the question, we see that we are interested in finding the rate at which the area of a circle is changing when the radius is 4. So we are relating the two, area and the radius. We know the area is pi r squared. We know the diameter is 2r, and we know the circumference is 2 pi r. Needless to say, we just need the area. I just wrote all those because we have to know what we need here. So the area is pi r squared. What is given? The radius of each circle is increasing at the rate of 3/2 feet per second. So dr dt is given. What do we want to find? dA dt. dA dt. At what point? When the radius is 4 feet. So here's how you write it. A is pi r squared. Given dr dt is 3/2 feet per second. If r is 4 feet, find dA dt. So A is pi r squared. The derivative dA dt is 2 pi r times dr dt. If we were to make sure everybody is comfortable with that, you can think of this as pi. So when you want dA dt, it's pi times r squared 2r dr dt. That's how you come up with the answer. And now we are going to plug in r is 4 feet, dr dt is 3/2 feet per second. Again, pay attention to the units. When you multiply all of them, you get 12 pi because these two cancels these two, right? Let's do that. So you have 12 pi square feet per second, precise answer. This is exact answer. Exact answer. And then you use a calculator and approximation. The ADT, the units of area over the units of time. And it proves it here because this is in feet, right? 4 feet. And this is what? Feet per second. When you multiply the units, you do get the proper units. So the units work always. Here's the equation 4x plus 3y to the power of 4 equals x squared. It says find dy dt. I mean, just right here, even if you don't continue, right here, you recognize t is the independent variable. And it continues that dx dt is 10, x is 4, y equals -2. So it is important to know the independent variable is t. This indicates that, which means the derivative of x is dx dt. So let's differentiate this with respect to t. This gives us 4 dx dt. This gives us 3 times 4, 12y cubed dy dt. So let's take them one at a time. So 4 dx dt. 12y cubed with the dy dt. X squared 2x dx dt. And at this point, you just plug in, but since we are interested in the value, plugging in will do the job. I want to show you both ways. First, we're just going to plug in. So we are done with calculus. Now, elementary algebra. Replace the dx dt with 10. Replace the y with -2. Dy dt, we don't have it. Same thing for the right side. This is 40. This is -8 times 12 is -96, and the right side is 80. We subtract 40 from both sides, and we divide both sides by -96. And we drop the common factor. We get -5/12. The common factor is 8. Now, this is fine, and we're done. I just wanted to show you, in case right here, we want to solve for dy dt. You don't have to do that. If you want to solve for dy dt, then you have to move this one. Let's move this. 4 dx dt goes to the right, becomes minus. And dy dt is the right-hand side divided by 12y cubed. But the right-hand side, we can factor the 2 dx dt. So the right-hand side is 2 dx dt times x minus 2. And we are dividing by 12y cubed. So this 12 goes away, becomes 6, and the 2 is completely gone. Again, do you have to do this? I just wanted to show you if you wanted to go through the process. This is just as good. You came up with the answer, and you're done. All right, again, the moment we see dx dt, that is telling us that t is the independent variable. And we want to find this for this equation. We're going to plug in to find out. First and foremost, let me put a raised dot here so we notice that this is a product rule. Now we're going to do them one by one. 3x gives us 3 dx dt. Now y times e to the power of x. We are using the product rule. Y gives us dy dt times e to the power of x. And then e to the power of x, it's e to the power of x times dx dt. Remember, it's not just e to the power of x because the independent variable is t, not x. So the derivative of this is e to the power of x dx dt times y. And of course, the right side is just a number, therefore it's 0. We're done. We just plug in. We're going to plug in. We are going to replace dy dt with -8. E to the power of x is 0. Let's plug in, and y is -1. So this is 3 dx dt. E to the power of 0 is 1. So this is 1. This is 1. So this is -8. And this is minus dx dt. 3 dx dt minus dx dt, this 2 can be combined into 2 dx dt. -8 moves, becomes 8 divided by 2 is 4. And we are done. But if we wanted to solve this for dx dt, then we have to keep this one, and we're going to move this because it doesn't have dx dt. And on the left side, we just take out the common factor of dx dt, left side. And now if we divide by the parentheses, we get dx dt. And now, of course, we got to plug in. Okay, we're going to plug in. If we plug in, we get the same answer. Because they wanted dx dt and we came up with the answer by just plugging in, that would be good enough. But this is in case. Again, the moment we see dy dt, t is the independent variable. And let's see how we differentiate this. Plugging in is not a big deal. We are interested in the first step, which is the calculus step. So you want to differentiate something to the power of 4. 4 becomes the coefficient. Then the same thing, whatever it is, to the power of 4 minus 1 or 3 times the derivative of the inside. This is the extended power rule. Remember that, the extended power rule. What is the derivative of the inside? 5x, 5 dx dt plus y, dy dt. Minus x minus dx dt. A constant gives you 0. Minus dx dt, and a constant gives you 0. You're done. Just plug in. So we are going to replace these values. X is 2. So 5 times 2 makes it 10. Plus -9, that means -9. 5 times dx dt is 3, plus dy dt we don't have, minus dx dt is 3. Just plug in. Again, this is 5 times 2, that's how we get this. 10 minus 9 is 1, 1 to the power of 3 is 1. So you have a 4, and this is 15. So you have 4 times 15 plus dy dt minus 3. So if you multiply the 4, you get 60 plus 4 dy dt minus 3. Needless to say, these two add up to 57. We take it to the other side and we make it negative 57. We divide both sides by 4, and that's the final answer. So t is the independent variable, and that's the key. Could somebody read this for us, please? Anyone? Falling sand is forming a cone-shaped pile. The volume of a cone is increasing at the rate of 54 pi cubic inches per minute. The height of the cone is twice the radius of the base. Find the rate at which the radius changes when the radius is 6 inches. So I hope you realize it's all word problem application. We need to understand what's going on. First and foremost is the shape of a cone. We have to know the relationship between the volume, the height, and the radius. So the formula is the volume is 1/3 pi r squared h. So that's a piece of information from geometry that we should know, or even you can say algebra, trigonometry. The volume is 1/3 pi r squared h. The volume is increasing at this rate. So dV dt is this much, 54 pi, and this is the unit, cubic inches per minute. The height is twice the radius, h equals 2r. What are we looking for? Find the rate at which the radius changes. That means find the RDT. When? When the radius is 6. Let me write all of that. Here's the relationship between the volume, radius, and height. Volume is 1/3 pi r squared h. The first piece of information here, dV dt is 54 pi cubic inches per minute. The second piece, the height, is 2 times the radius. Finally, what are we looking for? The RDT. At what point? The radius is 6. So I hope you see how we translate this into this mathematical language. Now, there are 2 variables here, r and h, but this will make it into 1. Because we are interested in dr dt, we're going to get rid of h. If we were interested in dh dt, we would get rid of the r. Since h is 2r, replace this. That's the first thing we're going to do, which is again algebra. So 1/3 pi r squared, and h is 2r. So their product becomes 2/3 pi r cubed. 2/3 pi r cubed. We are going to differentiate this with respect to time. Okay, the time, the units by any chance is given. Yes, it's in minutes, whatever the units are. So dV dt is 2/3 pi. Remember, 2/3 pi is just a number, 2/3 pi times. Now r cubed with the r cubed, 3r squared dr dt. 3r squared dr dt, and we can get rid of these 2. We get 2 pi r squared dr dt. So let's plug in what we have. We have dV dt to be 54 pi. The units, of course, cubic inches per minute. 2 pi times r, which means 6 squared, dr dt missing. So let's plug in. dv dt is 54 pi, 2 pi times r 6 squared, dr dt. Of course, this is 36, and then times 2 pi is 72 pi. We are going to divide both sides by 72 pi. And the pi's cancel out, of course. They are both divisible by 18, and we end up with 3/4 of an inch per minute. Take a look at the units. The units must always work. The units of volume over the units of time, the units of radius over the units of time. 3/4 of an inch per minute. So when the volume is increasing at a rate of 54 pi cubic inches per minute, the radius is increasing by 3/4 of an inch per minute. A 20-foot ladder leans against a building. The base of the ladder slips away at a rate of 2 feet per minute. Find the rate of change of the height of the ladder when the base is 12 feet from the building. So let's see what happens. So here's the building, here's the ladder. It's going to go this way, looking like that. So the tip of it is coming down. The ladder is fixed length of 20 feet. This is not changing. This is not changing. Okay. As it moves this way, it creates the speed dx dt is 2 feet per minute, or rate. As it comes down, it creates dy dt, the speed along the height, which is missing. That's what we are looking. So let's translate this again. First, understanding the setting. Now, what is given? Well, this is fixed at 20 feet. The base slips away at a rate of 2 feet per minute, so dx is 2 feet per minute. We want to find the rate of change of the height. We want dy dt when the base, that means x, is 12 feet. So what is the relationship between x, y, and c? Pythagorean theorem. A squared plus b squared is c squared, which means x squared plus y squared equals 20 squared in this case. So dx dt is given as 2 feet per minute. X squared plus y squared is 20 squared based on Pythagorean theorem. Dy dt is what we are looking for at the moment when x is 12 feet. So it's a simple differentiation with respect to t here. Of course, everybody knows this is 400, but we are differentiating for now. So this is 2x dx dt. This is 2y dy dt, and this gives you 0 when you differentiate. This is the only calculus step, class, the only calculus step. So we got everything. We have x, which is 12, dx dt, which is 2. We don't have dy dt, that's what we're looking for, but we don't have y either. So we have to go back to this formula and say when x is 12, what is y? So let's quickly find the value of y at the moment when x is 12 using Pythagorean theorem. Again, this is 400. You do the math. I'm assuming you can do that. You subtract 144 from that. You take the root and you get 16 feet. And so y squared is 156. You take a root, you happens. Now just plug it. You have everything except dy dt. Now, of course, 2 times 12, 24 times 2 is 48. 2 times 16 is 32. And so dy dt, so this one is we're going to divide both sides by 32. And that's, by the way, this is negative, but minus 48, right? Because 48 is positive, when you move it becomes negative. So minus 48 divided by 32, they're both divisible by 16, negative 3/2 feet per minute. Negative 3/2 feet per minute. What I want to explain is why this is negative. As it slips away, x gets larger. X is increasing. Dx dt is positive. As it comes down, y is getting smaller. Y is decreasing. Therefore, dy dt must be negative. And it is. We're going to look at the same situation. A 20-foot ladder leans against a building. The base of the ladder slips away at the rate of 2 feet per minute. Find the rate at which the angle. Now we want to look at something else. The angle between the ladder and the ground when the base is 12 feet from the building. In other words, we have the same situation. This is going to go this way. We end up with this. This is coming down. And we are in, and this creates an angle of theta. And as you can see, this angle is different than this angle. So this angle is changing as it slips away. We know dx dt is 2 feet per minute. We are looking for d theta dt this time. So we're going to write the same thing that we had before, the same as the previous page. Dx dt is 2 feet per minute. X squared and y squared, they add up to 20 squared. Remember that, the Pythagorean theorem. But this time we are interested in d theta dt when x is 12. So how do we come up with the answer here? We want to find a relationship between theta and the given. Since x is given, we rather find it between those two. Although we can calculate the y, and we already know y is 16. We can look at that, but since x is given, it's a better choice because there's always a possibility of making a mistake with the calculation. So what is the relationship is that cosine is the adjacent, which is x over the hypotenuse, which is fixed at 20. So that is the relationship between the two. I hope everybody remembers that. Cosine is the adjacent over the hypotenuse, whereas sine is the opposite over the hypotenuse. This is basic trigonometry. And so we can differentiate both sides. And before we do that, I want to make sure we understand this means 1 over 20 times x. In other words, This one, if you wrote it as 1/20 times x, is easier to follow. So if I differentiate cosine, I get minus sign. Remember that? Minus sign, cosine. You don't even have to look at that. Cosine gives us negative sign. And then you have to write negative sign of what? Theta. And then d theta dt, because theta is not the independent variable, t is d theta dt, and the right side 1/20 x. So 1/20 dx dt. So all you have to do, plug in and come up with the answer. And we remember that we have y equals 16. Okay. We said sine theta is the opposite, which is y over the hypotenuse. So is sine theta is 16/20. So minus 16/20 times d theta dt equals 1/20 dx dt, we know it to be 2. So one more time, minus sine theta is the opposite over hypotenuse, 16/20. D theta dt we don't know. 1/20 we write it. Dx dt we know it to be 2. We can cancel out the 20 from both sides or just cross product. Since the denominators are identical, we don't have to worry about them, which means minus 16 d theta dt equals 2. So d theta dt is 2 over negative 16 or negative 1/8. The units would be radians per minute. Radians per minute. In calculus, we use radians unless otherwise mentioned. We always use radians unless they mention about it. A spherical balloon is deflating, losing 8 cubic centimeters of air per minute. At the moment when the radius of the balloon is 20 centimeters, how fast is the radius decreasing? They may say changing, and then negative means decreasing. That's the idea. And we all remember that we've done a similar question. The volume is 4/3 pi r cubed. So let us write everything. And why am I, in essence, repeating the same type of question? Here's the reason. First, the volume is 4/3 pi r cubed. Then what is dv dt? Because it's losing air, it's minus 8 cubic centimeters per minute. And that's really the reason I wanted you to see that. When the radius is 20, when r is 20, we want to see what's the r dt. So I hope you realize this is being repeated. This is being repeated. The only thing I wanted to make sure, when we have deflation or losing air, that means negative. That's really the main reason. When r is 20, what is the r dt? We've done this before. We know that dv dt, again, I'm going to remind you, if I want to find dv dt, say 4/3 pi, and then r cubed, 3r squared dr dt, and you remember we had it done, 4 pi r squared dr dt. Now I'm going to just plug in. I'm going to replace the left side with -8, and I'm going to replace the r with 20. This gives us 400. So this is 4 times 4, 1600 pi. So we're going to divide both sides by 1600 pi. Both sides divided by 1600 pi. Eight becomes 1, 16 becomes 2. So minus, and pay attention to the negative sign, minus 1/200 pi centimeters per minute. It is important to know the units follow, okay, accordingly, dr dt, the units of the radius over the units of time. And this is the exact answer. And I'm going to emphasize this again. This is exact. So if they ask you for an exact answer, you use this. But an approximation, you change the pi not just to 3.14, but rather use a calculator 3.14159, and it continues indefinitely. And you use the number of decimals that they ask you. So negative 1/200 pi centimeters per minute precisely, negative 0.001592 centimeters per minute roughly. That's an approximation.